being able to make a comparison between different harvesters that perhaps are designed for different application areas might be something that you would want to do. And certainly you'd also want to be able to evaluate your own harvester and just figure out how good is it as a function of how good it could have been. In other words, could I really have designed this harvester any better for this particular application? And if so, how close did I get to building the optimal device? So there are lots of metrics that people have come up with in order to describe how good a harvester is. As I say, fights break out at the PowerMEMS conference as to which of these performance metrics is the right one. I think there's only one sensible metric, but I would say that because this is the metric we use at Imperial. Effectively, a figure of 100% on the scale that I'm going to show you means that that's the absolute best you can do. So I think it's a very sensible scale because it basically tells you if you get a figure of 100%, you've captured 100% of the possible energy that you could have done with the theoretical best generator you could have put into that particular volume. And so we call this thing the volume figure of merit. So let's have a quick look at how you calculate that. It's very simple. Ultimately, what we're trying to achieve here is a figure that tells you the useful power output of your particular design and implementation of harvester divided by the maximum possible power you could have achieved under those operating conditions with that particular size of harvester. That's ultimately the best you can do. If I give you a particular volume, we've already looked somewhat at how we optimize a device within a particular volume, how we set the right damping, how we choose whether it's resonant or non-resonant, what the velocity force characteristic of the damper should be, all of those things. Assuming we've made all the right decisions and we've chosen all of those things optimally, there will be a certain maximum amount of power that we can generate within a particular volume for the harvester. And so simply to calculate how good our device is, we simply measure how much power we get, what's its useful power output, and divide by that theoretical maximum. So let's just make sure we understand how we calculate what that theoretical maximum is. Essentially, what we looked at already, the basic expression for the power that you can generate from the linear device, is actually the best that you can do, or very close to the best that you can do. One thing that I haven't talked about in these notes, maybe it's worth a very brief discussion talking about it, is to start playing with the injection of harmonic forces into the system. When we're talking about these linear devices, we're talking about having typically a harmonic excitation at one frequency, and if it's a linear device, if it's the velocity damped resonant generator, then the mass inside the device is moving also sinusoidally because everything is linear. Actually, what you find is if you start to introduce some harmonic content into the forces that the mass is seeing, you're able to then effectively take away the movement of the mass at the peak of its travel and then effectively then increase the fundamental displacement a little bit more. So effectively, if you think about what I'm doing, I've got a mass that's moving inside a frame and it's going to be moving somewhat sinusoidally, and the strategy that we saw earlier was that I should basically design it such that I make exact use of the complete motion inside the frame. And if you look at that as being the kind of ultimate limit, then you can do a calculation straight away and you can say, well, that's actually the maximum power based on the density of the material I use for the mass. That's the total amount of power that I can generate with a sinusoidal movement inside a box of a specific size with a particular volume. Depends on the frequency, depends on the density of the mass, depends on the acceleration of the vibration source. You can very quickly do this optimization, again, that I mentioned to you earlier. If you make the mass bigger within the volume, the mass can move less, but the mass is bigger. If you make the mass smaller, it can move more, but the mass, of course, is smaller, and you're interested in force times distance. An exercise for you guys to do, which is fairly straightforward, is to prove that the optimum value of the proof mass is one which occupies exactly half of the total volume of the device. So if you've got a device which is this long, you should make the mass this long so that half of the volume is dedicated to the mass and half of it is dedicated to the movement of the mass. And this is something that you see quite often that is not implemented correctly for an optimization in terms of the way people build these devices, because people will tend to go for more movement and less mass. But actually you want to be filling you know, half of the total available volume with mass and half of it left for the movement. But if you've done all of that, then this is effectively the formula that you get. We'll talk about that in a little bit. There's something that we do, however, in power electronics, which is actually somewhat beyond the scope of the power electronics that I'm going to talk to you about in the next slides and the next slide set. But it's something that we call third harmonic injection. And I mention it here because I hope you'll understand this in the context of the mechanical system and understand how you can get a little bit more power out of these devices by adding in some harmonic forces. So you remember, I'm sure, Fourier analysis, and you remember how to build a square wave from a set of sine waves. If I want to turn this sine wave into a square wave, I start adding in third harmonic, fifth harmonic, seventh harmonic, etc. And the strategy, of course, then is always to try and add in the next harmonic that makes this wave look a bit more square. And to make this look a bit more square, I need to add in a third harmonic which increases the gradient at the edges here and pulls the top down a bit. So I end up with a third harmonic that I add in that looks like this, and then I'm adding in this type of, so I'm not drawing it very well, but this type of third harmonic, which is basically cutting the top off the fundamental and therefore sort of squashing the wave a bit but making it a bit squarer. So I end up with, to a first approximation, my sine wave has gone from this to this. And if I add in the correct amount of third harmonic, what I'm able to do is effectively flatten off the top of this waveform so that instead of doing this, it does this. So it's displacement. If this is now displacement that I'm thinking of, and this is the displacement of the mass that is moving, then the fundamental component of this waveform here, that's a little bit shorter because the top is being taken off it by the third harmonic, the fundamental component of displacement is the same as it was here. But the actual distance that is being traveled by the mass overall is a little bit less because the third harmonic is cutting that down. So what I can do to effectively try and increase the displacement of the fundamental in my system is to add in a little bit of third harmonic, pull the amplitude of the system down a bit, and then decrease the damping factor a little bit in the fundamental to allow the new motion to expand to cover the entire range of motion. Remember, what I'm trying to do is maximize force times distance. And if I can move only between my mass, between two boundaries, if I move sinusoidally between those two boundaries, I end up with a motion like this. If instead I add in a little bit of third harmonic and I pull the tops off here a little bit, I can then increase the fundamental value a little bit more and hit the end stops. And crucially, as long as I've got a fundamental force at a particular frequency or a fundamental motion at a particular frequency, any harmonic content that I've got in there doesn't actually contribute to the generation of real power in a positive or a negative sense. So if you think about this purely in electrical terms, what it means is if I've got a voltage source at a particular frequency, I could only get real power from that voltage source if I pull a current at the same frequency. And you know that if you pull a current at the same frequency, if it's 90 degrees out of phase, that also means no power. That's like just putting a capacitor onto an AC waveform. There's no real power transferred. But if you have a voltage at one frequency and you pull a current at a different frequency, then there's no real power transferred. It's just energy sloshing back and forth. I can play exactly the same trick on the energy harvester. I can take my fundamental displacement waveform here and a fundamental force. I can add then some harmonics into the displacement waveform, allowing me then to pull down the overall displacement, but then maximize again and increase the fundamental value in order to then get a little bit more power. And the harmonic content in here, assuming still that I'm exciting the device with a pure harmonic tone, the additional harmonics here simply don't matter. There's a little bit of energy sloshes around, but it doesn't really affect the real power that you can generate. You can generate a little bit more real power because the addition of this harmonic lets you expand the fundamental a little bit and still remain within the displacement constraint. It's a little bit counterintuitive, but it's basically something that we use a lot in power electronics for expanding the headroom slightly in the circuits that we use to drive electric motors by injecting an additional harmonic content, reducing the overall magnitude of the voltage, and then scaling the fundamental up again back to the original constraint. So it's maybe a little bit more, well, it's certainly a little bit more than I've been explaining so far in this talk. I'll give you a reference for this. Some work we did recently with Einar Halvorsen in Vestfold University College in Norway, looking at shaping the damping force a little bit more finely and coming up with this sort of argument. Assuming we're not playing around with the harmonics in that way, let's assume that we've got pure sinusoidal excitations and we've got sinusoidal damping forces. We then do that optimization that allows us to figure out that the mass occupies exactly half of the swept volume in the device, and so I can then calculate at resonance the amount of power that I can generate. So that gives me an upper limit, and so I can calculate my volumetric figure of merit, useful power output divided by that expression. You then look at what is available, what has been available in the literature, and see how well people are doing on this particular figure of merit. Now, I mentioned earlier, and this is a question that you asked about which of the devices has been best, which has overall looked good in research, which is good in industry, all these sorts of questions. And I mentioned this group from the University of Tokyo. I do somewhere, and I should have updated it in here, and I'm sorry that I didn't, have an updated version of this plot, which has got some of the newer devices on it, where the effectiveness values are way better than this. They're a factor of 10 better than this in some of those devices. But the trend still is that the effectiveness values, or the figure of merit, volumetric figure of merit values, for the vast majority of energy harvesting devices are down in the single %, suggesting that if we built the devices better, we could potentially do 100 times better than what is being typically demonstrated. Now, as I've said, University of Tokyo has managed to step these devices up by a very considerable amount, and so the bar has moved. We have to now do a lot better. A few years ago, if you got 1% for your device, actually you were doing reasonably good. If you were getting 2, 3, 4%, you were doing excellently. University of Tokyo has managed to push these figures into 20, 30, 40, 50%. So I would strongly suggest actually that you have a look at some of the papers from the University of Tokyo, from Yuji Suzuki's group, as to how they've been building some of these devices. They've been doing a very good job. Okay, so just to summarize where we've got to in the analysis so far, and then we'll start to look a little bit more at system modeling and also at a sort of preliminary look at the electronics for these systems. So what have we done so far? We've basically said we've got this that we're going to put a harvester in. We've used what is the so-called mass in a box model of an energy harvester, and we've looked briefly at how we go about maximizing the performance. In order to do that, we broke it down into several different types of energy harvesting device, resonant versus non-resonant, and we looked then at the fact that we have linear or non-linear damping. And that allowed us to generate a whole bunch of equations and to plot the relative performance of those devices. We saw that we basically got very good advantage from having resonance when the device is larger than about 10 times the driving displacement amplitude. If the device is bigger, significantly bigger than the amplitude that is driving it, then you get this resonant gain. If that's not the case, then there's not very much benefit to using resonance. In fact, there's only a detriment to using resonance, because if you end up operating below the resonant frequency, as we saw, the power falls off very, very dramatically. So if you've got a device where the vibration is small and the device can be big, then you definitely should use resonance. If it's not the case, then you probably shouldn't, because if you do use resonance, you're not getting much of a benefit from it. But if you end up tuning so that your resonant frequency is above the frequency of operation, then you get very little power at all. Okay, so let's talk now a little bit about system modeling, and this kind of goes back to the work that you were doing yesterday in LT Spice. So everything that we've done so far here has basically been involving closed form algebraic solutions in order to get all of the plots. And in order to do that, we knew the characteristic of the damper. We either knew it was linear or it was a Coulomb damper. We've got to take into account this coupling between the mechanical and the electrical system. That's very, very important, and if there is no coupling, then of course there's no generation of power. The question is, how do we go about generating a model for this that we can use in computer simulation that lets us perhaps spend a lot of time evaluating circuit performance, but also lets us understand the behavior of the mechanical system when we've attached a circuit to it. So what we're not going to be doing here when we start building power electronics as the interface circuit between the harvester and the load, what we shouldn't be doing is designing and simulating that power electronics in isolation, because the behavior of the power electronics is going to then affect the behavior of the harvester, which is going to affect the electrical output of the harvester, which is then going to affect the behavior of the power electronics. So you can't really do these things completely in isolation. I mean, you can get some indication, but you really need to be analyzing complete systems. So one of the things that you can do if you wanted to do a very basic simulation of this type of system is to just put the differential equation into something like a Simulink model. And here you can see actually this is a Simulink implementation of the CDRG, where we've got obviously this chain of integrators here, which is as we would typically expect when we implement a second order differential equation in something like Simulink. With some feedback terms here, there's the resonant frequency that's being fed back, and there's also the damping force here, which is in this case the force multiplied by the sine, in this case of the velocity, which is being taken off at this point. So that, as a sort of basic model there, is exactly the basic model of a CDRG, assuming you know what the force is. And the key point, and what we want to bring out in terms of simulation of these systems, is that force is now going to be something which we're going to control from the electrical domain. So this is a very basic model, mechanically, of differential equation of this nonlinear resonator, or of a spring with a nonlinear damper. But crucially, the force, the damping force, is now going to be determined by the voltage on the plates of the capacitor. And the voltage on the plates of the capacitor, of course, then is a function of both the circuit design that we use and the way that we operate the circuit. And we can try and set that to an ideal value. And then the question is the circuit good enough to allow us to set the conditions to the value that we choose? Or will it be somewhere close? How accurate will it be? Will there be a leakage current? All of these things we would need to start to explore to really understand the overall behavior of the system. So we'd like to have a way of doing a proper time domain simulation, both of the mechanical parts of the system and linking this electrical force here back through into the electrical system and seeing the coupling between the two. So one of the simple ways of doing the modeling here, and I think again this is something that Michael showed you yesterday, was that there's a well-known mapping here between mechanical components and electrical components. And this is a very nice and quick way of putting models into a circuit simulator that are mixed electromechanical models. So if you take a bunch of the simple mechanical components here that you might want to simulate, spring, mass, and a damper, these have nice mappings into their electrical equivalents of an inductor, a spring, and a resistor. There are two well-known conventions for doing that mapping between mechanical and electrical components. This particular one is it's called flow to voltage. There's one which is called effort to voltage. Basically, you break down all these sorts of models into two components, two conjugate power variables, as they're called, the two things you multiply together in each domain to get power. And of course, in an electric circuit, that's current and voltage. In a mechanical system, it's force and velocity. And you've got to decide whether you're going to equate velocity to voltage or velocity to current, for instance. And you can do it either way, but depending on how you choose to do it, that changes the mapping between the mechanical and the electrical components. But you can do this quite nicely, and of course, if you've got this very simple mapping, then you can produce a SPICE simulation that is extremely fast to run in a circuit simulator, modeling the mechanical system here. So there's a current source, in this case, modeling the mechanical excitation. There's a spring, there's a damper, and there's a mass, all modeled as electrical equivalent components. And then we have to then be able to map the behavior of the mechanical domain into the electrical domain, and we do that typically through the transduction mechanism, of course, and the transduction mechanism then needs to have some turns ratio on it, like a transformer, in order to be able to map, in this case, the velocity, for instance, which is voltage across these components, into generating a current or a voltage in the electrical domain. And depending on whether we use an electrostatic transducer or whether we use a piezo or electromagnetic, that will change the turns ratio present on this transformer here. But this is quite a nice way of being able to do a model of the mechanical system and the electrical system, have them properly coupled together so that any currents that flow here in the electrical system also give you a force back into the mechanical system. And of course, at this point now, this is a simulation, in this case, of an electromagnetic type of harvester with a certain amount of inductance on the harvester's coil and a resistive load and the mechanical system. If I now put a different type of circuit onto here, not just a resistive load, I could put a rectifier and a battery, I could put some switch mode power electronics into here. This will then, all the forces associated with the currents that flow due to the existence of whatever actual circuit I put on here will flow in here, will be referred back through this turns ratio of the transformer, and will give me the motion of the mass in that system accurately. But it's all done in the electrical domain with mechanical equivalence, so it's very nice from a perspective of implementing this in SPICE. Example here of a piezo harvester, so there's the electromagnetic harvester with the inductance in the output. Modeled typically as a parallel resonance system. It's easier to model the piezo system typically with a series resonance system here, voltage source excitation, and then a capacitive load on the output here, which is the capacitance of the piezoelectric transducer. And at this point then again, that resistor can become whatever circuit I want it to be, and I can get a complete model of the mechanical behavior and the electrical behavior that are coupled when simulating this system. That's probably, is that what you were using yesterday with Michael Lalart in the simulations? Yeah, that was the basic setup. And then you were starting to put, at the end of the session, you were starting to look at doing something other than just putting resistive loads onto here and this more complicated switching arrangement, which we'll talk about in a bit more detail. And I hope to give you some insight into really what's happening with those switching arrangements. If you want to go more sophisticated, because of course this is assuming a very linear mechanical system, and that may not be the case. You might need to implement springs which have nonlinear behavior. You might want to model what happens in terms of the maximum deflection of something. It hits the end stops in the device, the mass smashes into something. All of that behavior you might want to model, in which case you end up with perhaps something that is a little bit more complicated, looks a little bit more like a Simulink type of simulation where you're just implementing equations in a graphical sense. But you're able to do that in something like SPICE so that you can then properly simulate the electrical circuit and this co-behavior between the electrical and the mechanical system. So we did actually, a number of years ago at Imperial, we made this toolkit for SPICE, Imperial College Energy Harvesting Toolkit, ICES. If anyone's interested in using that, I'll dig that out. I'm not sure if it's still available for download on the web, but of course I've got a zip file of it somewhere, and it's got a whole bunch of components in it that let you simulate different types of harvesters. So there's a mass spring damper model, there's different transduction models that go into SPICE here, parasitic damping, and of course you can add onto the electrical terminals here anything that you want in terms of circuit simulation. So if you want to have a quick look at the behavior of a device, but you don't want to get into the nitty-gritty of doing all the modeling yourself, you might find that this toolkit actually is a good way for you to get started doing modeling that is a bit more detailed than the modeling of this type of approach, but you don't have to get hung up on the implementation of everything. Do you have a question?
Yeah, I don't know if I'm getting ahead of the subject that you are introducing to us right now, but I'm working in some of these things that you're telling, and one of the main things that really concerns me, because maybe I cannot see, is how can we manage the losses between the relationship of the mechanical system and the electrical system? I don't know. This thing has been concerning me a lot, so I don't know if you have an answer for me in this case.
So, yeah, I think the thing that makes this what you're saying probably is exactly the thing that makes all of these optimizations very, very difficult, because you can move things around, you can make something better, you make something else worse. The exact relationship between different aspects of this system are really quite intricate. So we did some work recently in collaboration with UC Berkeley, looking at the complete optimization of a piezoelectric system. And that was trying to optimize everything from the shape of the cantilever, how big a mass you put, how much flexing of the cantilever you could have, all of these things, plus the optimization of the electric circuit. And the optimization of the circuit then included things down to the detail of the doping profile in the MOSFETs that we used as the switches. So we did this massive optimization on all of these things. And we got a bunch of results, and I'll share the paper with you. How accurate the results are is very dependent on exactly what you think the state of technology is in all these different areas at any one time. So if you can build a MOSFET that's got half the leakage of another MOSFET, that'll change the results very considerably. If you've got a piezo film that can have double the coupling coefficient or can have double the flexing of a previous film, that will massively change the results. And so our approach to this was essentially to just simply try and model everything, because it was quite amazing at just how much tweaking a small parameter in the electrical domain would end up changing the overall system optimization and reflecting potentially significant changes in the way the mechanical domain operated, to try and get to account for that limitation in what you were seeing in the electrical domain. So this modeling, as you see here, is kind of a first step into doing that, but it's certainly not a complete optimization. And all of these quite significant optimizations that we had to do, they have so many degrees of freedom. So it is, I'm very happy to chat to you about this offline. It's something that I guess the community still hasn't properly addressed this, I think. Because it's not a traditional system that you can do an optimization in a relatively discrete way by taking one box and optimizing it and taking the next one and optimizing it. It's very well linked, and it's very difficult to say that you can assume that any of those boxes is anything like ideal, which makes it very difficult to do that optimization. So when you say that you've got losses in the mechanical system, losses in the electrical system, how do you know where you should move the losses to minimize the overall loss? Without kind of writing out all of the equations and doing a complete coupled optimization, I don't have a better way of doing it at the moment. And doing it the long way is certainly a long task. It's probably, I've said to my co-authors on that particular paper, it's definitely the most involved paper that I've been involved writing, and it took us probably 3 years of solid work with 2 or 3 people working on it. So maybe we can have a bit more of a chat over lunch about that. Not to put everybody off, it's a very interesting topic, keep going with it. But when you look into the specific optimization of the whole system, because everything's so linked, it is a very challenging problem. This is really a kind of first step into looking at the linking between the mechanical and the electrical system that goes beyond this very simple modeling approach. But if your focus, for instance, as part of this project is looking at just the performance of the electronics, this type of modeling might be suitable. It might contain sufficient information that you need in order to be able to design the electronics. So let's talk a little bit now as, before we start looking at the fundamentals of some power electronics, I want to talk to you about the basic overview of what you need on the transduction mechanisms. Yes?
Sorry, just before, what about the Coulomb damping when you try to make some model like what you show?
Yeah, so this particular toolkit that we've produced here has got models in for the various different damping mechanisms. The difficulty, particularly the difficulty simulating Coulomb damping, is that you get a sort of stiction where the thing will move to a certain point, and then in the simulation environment you get lots of zero crossings, which will slow the simulation down quite a lot. So that generally means that the linear systems are going to be quicker to simulate, and that once you start adding in these nonlinearities, simulation time can balloon. Yeah. But it's all in there in this toolkit. You've got linear, non-linear dampers, different implementations. You've got piezoelectric transduction, electromagnetic, and electrostatic. Feel free to have a play around with that. So let's talk a little bit now about the interface requirements. We want to move away from just thinking about energy harvesters as having resistive loads. And many people, when you see the discussion of energy harvesters, they'll have the harvesting mechanics and the transducer, and they'll put a resistive load on it, and they'll measure how much power they can get into that resistive load. And of course, that is an indication as to how much power that system is able to generate, but in reality, you don't want to be putting the power into a resistor. You want to be rectifying it, and you want to be storing that energy probably in a battery or a capacitor. So let's have a think about that. So what do we need to be able to do here for the different types of transducer? What are the requirements? It's not only about, as I've alluded to, it's not only about the requirements that we have specifically to get the electrical power out, excuse me, in the way that we want. Most of these systems that we're talking about for energy harvesting, certainly motion harvesting, are going to be producing sinusoidal outputs. If it's piezo or electromagnetic, it's going to be producing an AC waveform. We've got to rectify that to be able to power any modern electronics from it. And that's one of the sets of requirements. But the other set of requirement is not looking forward to the electronics, but looking back to the harvester. How do we get the optimal force on the harvester to maximize the power density? And that's also something that the electronics should be able to do. So we've basically got to think about here, how do we get the right force characteristic? We can potentially, by putting the electronics on there, change the force velocity characteristic, both its shape and its magnitude. And so we have to think about the way that we do that with the electronics. So effectively, this is the sort of system that we're now thinking about. We've got our transduction mechanism with our mechanical model. We've then got our circuit here, which is interfacing to the transducer. Part of the capability of that circuit is going to be to do rectification in most circumstances, but another significant part of its capability has got to be to make sure the transducer sees the right force to give us the maximum possible power density. There's going to be some energy storage in the system, almost certainly, to cope with intermittency in the vibration source. If that storage is a battery, then maybe its voltage is fairly well fixed, and I could potentially power my load electronics, my sensor, my communication directly from that storage element. But if it's a capacitor, its voltage is going to be swinging up and down quite a lot. And so then there would then need to be some regulation of that voltage before I power the load. So from an electromagnetic transducer perspective, let's think about that. The generator from the voltage typically is relatively small, so probably needs to be stepped up. I've got to draw a known current from the generator, because if I change the current that I pull from the generator, I change the damping force. So I'm going to analyze my mechanical system. I'm going to say, okay, in this operating mode, this is the size of the harvester, this is the excitation from the mechanical vibration, and I can work out the optimal force to maximize the power generation capability of that mechanical system. If I'm going to do that, work out that optimal force, that translates to a particular current in the coil. And so that means that my circuit that I attach to my harvester, I've got to be able to control the amount of current that I pull from the harvester so that it basically mimics a resistor, and I can dial in the value of the resistor via some control loop. So I need basically a power converter whose input resistance I can control to make a linear damper. And at the same time do rectification. Now there are lots of ways of doing this, and I've got more slides on this in the next set of notes once we've done a basic primer on power electronics. But just to give you an indication here of one of the circuits that you might use for an electromagnetic type generator, here's our generator, simple AC waveform, and the inductance here of that coil. What you would typically see here is people would simply put at this point, between this point here and this point here, they would put a full rectifier, 4 diodes. They would therefore convert the AC into a DC, and they would put a smoothing capacitor. And they would say, okay, that's it, job done. I've done the electronics for the harvester. The problem with that is that at that point you have no control as to the current that is flowing in the harvester. And that basically means controlling the current in the inductance of the harvester and the current in this source here. Also, if you have a full wave rectifier, you have to overcome 2 diode drops to turn those diodes on. So depends on the diode technology you're using, but you're probably going to need at least half a volt going up towards a volt to get those diodes turned on. And with a small harvester, it might be difficult to achieve that voltage. So the solution here is to use a back-to-back converter arrangement, and we'll look at this converter in more detail in the next set of notes. But effectively, in power electronics, what we're trying to do is to control the voltage on capacitors and the current in inductors. Those are the 2 things in power electronics that we would like to control. If we're building a power supply, we're often wanting to control the output voltage, and irrespective of how much current we draw from that power supply, we want to make sure that it's always got 5 volts on it. So there's a control loop which is controlling the voltage on the capacitor. In other circumstances, particularly on the front end of this system with a harvester interface, then we're interested in controlling the force that the harvester sees to maximize the power density. And that means then that we can control the current in an inductor. So those things are the 2 sort of variables that we like to control in power electronics, because they're the things that alter fairly slowly. Voltage on a capacitor changes slowly, current in an inductor changes slowly. So they're the 2 things in power electronics you can control, and they fit very nicely into optimizing the behavior of a harvester, controlling the voltage on the output here to supply the load electronics, and controlling the current in the input inductors here to control the force on the harvester and maximize the power density. Okay. The difficulty with the electromagnetic transduction mechanisms, yeah. 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 So typically what we tend to see now, and I've got more information on these circuits in the next slideshow. But what we tend to see is that it's possible to build the control circuitry for these devices running off maybe 10 microwatts, that sort of order. Now, if your overall harvester output is going to be less than 10 microwatts, then you wouldn't be able to use a sophisticated control scheme. Once your harvester output gets above that, if you've got a harvester output that's pushing 100 microwatts, that sort of order, then probably the benefit you get by having a more sophisticated control scheme and being able to control ultimately the force on the harvester by controlling the inductor current or by controlling the voltage on the piezo material, there is clearly a control overhead associated with that. But once you get to something like 100 microwatts, then probably introducing that more complex control scheme buys you more back than you're investing. If you've got something where your power requirements or your power capability from the harvester is just extremely low, then yes, at some point you say, well, I can't implement any control scheme. You end up doing everything passively with diodes, and you have something that probably the performance is quite poor, but it's probably the best you can do based on that power generation capability. There's an additional issue associated with this, which is how do you start the thing up in the first place? You need power to run the control circuitry, but when the thing is starting up from cold, there's probably maybe no voltage on the output. So you probably have a passive startup scheme which bootstraps the active scheme. Yeah? So you can either include it or not. And people, when they specify the effectiveness, should be very clear about whether they've included the electronics or whether they haven't. Okay, the electrostatic transduction mechanism. I just want to show you very briefly some electronics that you can put on each transducer, because in the next section of the notes here, we'll have a lot more detail on power electronics. And I'm aware that most of you probably don't have much of a background in power electronics, so I want to really look at some fundamental issues so you really understand where we're coming from with this. The difficulty with the electrostatic transducer tends to be that the capacitance values are very small, the total amount of charge we're dealing with is very small, and the voltages typically are really quite high. And that means that any transistors that you've got that you're operating in your circuit and the blocking junctions, any blocking that you do in terms of turning off a switch electronically in electronics and in power electronics is effectively just a reverse biased PN junction, like a diode in reverse bias. And it requires a little bit of energy to reverse bias it. You know, hopefully you remember that when you put a diode from forward conduction into reverse bias, it goes through a process called reverse recovery. It has stored charge in the PN junction when it's conducting in forward current, and in order to put it into reverse bias and stop it conducting, you need a small amount of reverse current flow to discharge the junction and to build up a blocking voltage. All of these things that you, in a circuit that's processing hundreds of milliwatts or watts or kilowatts, they tend to be inconsequential. Well, then you have to think about them in terms of losses and heat dissipation, but in terms of fundamental operation of the circuit, you don't really worry. In a harvester, these bits of energy you need to make the circuit switch on and off can be really fundamental as to whether you can make something work or not. So we looked at some circuit optimizations where we were literally looking at optimizing the width, length, and doping ratios of the MOSFETs to get the best overall performance out of this type of electrostatic harvester, knowing that the variable capacitance was extremely small, the total amount of charge we had available was extremely small, and that basically means you end up, if you're designing this sort of energy harvesting system, now we've got to know something about mechanics because we've got to understand the mechanical system. We need to know something about materials if we need to make the piezo elements, and we need to make it good. We need to build some electronics that we're going to attach to this, because as you've seen, the behavior of the electronics and the way the electronics can influence the mechanical system is critical. And so we've got to be able to understand the electronics to be able to build an optimized system. But if we're going to then build the electronics for systems that are so sensitive with such small amounts of charge, we end up then even having to look at the specific design of the MOSFETs as well. Which again, comes back to what I said yesterday. That's why this is such a fascinating topic, because everything is so interlinked and it's such a multidisciplinary problem. Okay, so we had a look at basically designing circuits for the electrostatic case to try and vary the voltage that you see on the capacitor and set the voltage to the right one, which gave you the optimal force to maximize the power density. And then on the piezo, let's look in a little bit more detail at what's happening with the piezo transduction mechanism here. This is directly relevant, of course, to what we're doing in ENHANCE. So the very simple scenario for dealing with a piezo transduction mechanism and getting a voltage out of it that you could power a load circuit is to take the piezo transducer here with the current source and the shunt capacitance, put that through a full wave rectifier onto a smoothing capacitor, and you get some sort of DC voltage out. And I think this is probably one of the first circuits that you simulated yesterday in LT Spice. The difficulty with this circuit is that there is no clear way here to be able to control the voltage on the piezo material. And remember, on an electrostatic based transducer, which could either be implemented with a piezo material or with a parallel plate capacitor, it's the voltage on the transducer that is going to influence the force that the mechanical system sees, and we've got to optimize that force to maximize the power. So we've got to be able to control the voltage on the piezo device to make sure we can operate it at its maximum power point as a system. Now, if you have this sort of system here, the only way you can control the voltage that you see on the capacitor is by directly controlling the output voltage here. And you might not want to do that because this output voltage is feeding the load, and you want to probably decouple the voltage that the load sees to the voltage that the transducer sees. In addition, with this circuit, it's got two diode drops that I have to overcome. And with low piezoelectric coupling, probably this circuit is quite hard to achieve a damping which is high enough to get the power that I would be able to achieve as a function of my volumetric figure of merit that I talked about earlier. And this is why, based on what Michael told you in the later part of the lecture yesterday, this type of interface is not something that you use to get really good power levels. And he showed you circuits where you get significantly higher power levels than you can with this simple circuit by being a little bit more shrewd with the way that you operate the circuit. And this is effectively what he showed you yesterday. So he showed you something that effectively flips the charge on the piezo at different points in the cycle. He probably showed you this circuit, exactly this circuit that the guys that come from Garamar's group and have been related to Daniel Garamar's work call synchronous switched harvesting on inductor. And the basic concept here is, rather than just take the raw output of the piezoelectric material, which is sinusoidal, put it through a bridge rectifier and put it onto a capacitor, the basic concept is to say, well, that sinusoidal voltage that I'm getting out of this piezo If I, at the time that that piezo gets to the peak of its direction of travel, flip the charge on the piezo to the opposite polarity, so I build up a maximum voltage on this capacitor because the piezo flexes into one position and it stops briefly at the top of its travel. That's where it's got maximum voltage on it. If I didn't touch that voltage now and I allowed that piezo to flap back down to the bottom, I just simply see a sinusoidal voltage appearing on that piezo material. But instead, I allow the transducer to flip up to the top. It generates a peak in its voltage at this point. If at that point I now close a switch with an inductor onto that capacitor, and I allow the charge on that capacitor, which was giving me plus V, to now invert itself through this resonant circuit, so I go from plus V to minus V. Now, when that piezoelectric material moves down, the voltage decreases, it becomes more negative, but because I'd started it from a point, it becomes more negative, and the amplitude, therefore, of the voltage builds. I get to this point here, piezo's at the bottom again, and I flip the charge again, so the charge becomes all the way positive again. Then the piezo moves up again and adds to that positive voltage. And so in such a way, I get this increasing envelope here. There's a finite amount that envelope can grow because of losses associated with doing this charge flipping. But I can get much bigger voltages on the piezo than I would have done if I just allowed it to oscillate in a purely sinusoidal fashion. So why is that inherent in giving us more power from this system than if we just allowed the system to oscillate with a pure sinusoid? Well, you can see the voltages are bigger, and probably anything on the same system with a bigger voltage is going to give you more power. That's not a very rigorous argument, though, is it? If you think about what's happening, I'm not sure if I've got the... No, in the next slideshow, I've got a bit more of an animation about this. But let's give you a bit of a teaser for it here, so that when we come to see it next time, maybe it'll make complete sense to you. What is happening effectively when the piezo beam bends upwards is it is getting a charge displacement on it and a voltage on the capacitor, which is tending to try and pull that piezo material back to its central position. It's a spring which is being deflected. There's a spring constant inherent in that material and the beam and the substrate, which is trying to pull it back to the center. But the creation of the charge displacement and the voltage, therefore, on that piezo is also pulling it back in the same direction. So if instead of allowing that voltage to just oscillate sinusoidally, I chop the voltage and have it behave like this, going from one point to another, switching the voltage, what am I effectively doing? I'm saying, well, the voltage, my piezo beam bends up, which is this first part here, gets to the top of its travel. At that point, this voltage here is actually acting in a way on the piezo to try and pull the piezo back to the center. Instead, if I get to the end and I flip the charge on there to the opposite extreme, what am I doing now? The force on the piezo due to the voltage is trying to push it further in that direction. So now, because of the inertia of the system, the piezo beam is going to move downwards because that's what's happening in terms of the mass and the input acceleration. I'm able to basically have a higher force. I'm doing work against the mechanical motion because I started here, I displaced the piezo to this point, and the voltage on the piezo was trying to pull it back to the center. But when it got to its extreme, I flipped the charge, so the voltage now is actually trying to push it further in this direction. But now the mechanical motion pushes the beam in this direction, so the force that I see on the system would have been. So I'm now able to do a bigger integral of FDR over the movement of the device because the force has been made bigger, because I've intentionally flipped the charge at the end of the travel such that the force that I'm doing work against has been made bigger than it would have been if I hadn't done that charge flipping. That is basically fundamentally what is going on with these funny waveforms where I cut up the flip the charge at the end of the waveform. I'm basically allowing the piezo to give me more resistance to the movement, so that over a fixed maximum movement, and I'm going to be constrained with the maximum movement because it's a piezo beam, it can only move a certain distance before it fails, so I've got a very limited range of movement. So if I want to get the power up, I've got to get the force up. So to get the force up, well, I can now basically force myself to set voltages on the piezo so that the piezo is inherently trying to resist the movement of the device in the next direction that I know it's going to move in. So I've got to then synchronize this with the movement, but as long as I can do that, and I can, then I can get significantly more power out of this device than if I don't chop up the voltage like this. And the simple way of implementing it is shown here, which is what you were shown yesterday afternoon. There are more sophisticated schemes. And the interesting thing, when you start breaking the voltage up like this, and it's quite nice at this point to be able to link this piezo harvester back to the work we did before the break, looking at optimizing these different architectures of generator, you find that when you apply this type of switching to the piezo, it is no longer a linear system, as you might expect. The force now has these changes at these discontinuity points here. But actually what you see is that this piezo with this switching scheme now is actually a Coulomb damper. So this is actually a CDRG now. So we can use all the analysis that we've done for the CDRG and map it directly onto a piezo material, assuming that with the piezo we're going to use this SSHI type switching scheme. And that then means that effectively we've traded operating with this scheme a VDRG type of operation of a piezo material, but where the damping is very, very limited. We've made the system a bit more complicated. We've changed it into a CDRG, but we're now able to get much more force from the device by being able to put much bigger voltages onto the device. So we've gone from, if you like, a weakly coupled VDRG to a much more strongly coupled and controllable CDRG. So that again reinforces the fact that don't think of the transducers themselves as behaving in a particular way, and that this type of transducer is linear, this one is not linear. It depends on both the transducer and the operation of the circuit that is connected to it. This is a circuit here that we've used at Imperial to implement this switching scheme as being something that it uses more transistors than the SSHI approach, but actually halves the losses. I won't go into the details of this because I think we should probably look at the power electronics stuff before we look at this in more detail. Okay, so let me conclude this section of the notes, and then we'll have about 10 minutes before lunch, which is perfect for me to just give you a bit of a teaser for what we're going to do after lunch on power electronics. So motion-driven harvesters are still something of significant interest in the literature, largely because we're still a long way from optimizing these things. I think from the sort of applications perspective, clearly people want these devices. Lots of people in industry want these devices, lots of consumers want these devices, they want to get rid of batteries, they want things to be self-powered. So there's really an application pull to have these harvester devices work properly. But then from the research perspective, it's still a very interesting problem because it's really quite difficult. And people in general are struggling to get anywhere close to optimizing these devices properly. We have, in recent times, as I've said, had pretty good results from the University of Tokyo in terms of optimizing these systems. It's an electret-based system. It's very difficult to manufacture. They have obviously got exactly the right expertise in that lab in Tokyo to produce very nice systems. And it's something that they've been working on for probably around 20 years now in that lab in total. So it's nice that we're finally starting to get some better results through for these systems. But in general, the performance is not as good, anywhere near as good as it could be. And so I guess the point that I really want to make from this first presentation is that the system is really important. And the link between the mechanics and the electrical part is very important. And even if you're a materials person working on materials development, it's important that you understand how the changes in the parameters in the materials will affect the mechanical behavior of the harvester, and ultimately whether that will then affect the circuit design that has to interface with the harvester. Because if you start doing stuff from a materials perspective that looks brilliant from the perspective of the piezo film and maybe makes the mechanical system look great, if at the same time you make the electronics that connects to the system impossible to design, then there's no point in working on that film. So you've got to have some appreciation of the whole system here so that you don't design yourself into a corner with optimizing something that does really well for one subsystem and really knackers the other subsystems. So finally, why is it difficult to make a self-powered wireless sensor node? And why was Seiko so clever in terms of what they did with the Seiko watch? And I alluded to this a little bit yesterday evening. If you take, so here's a basic plot for looking at the power that you can get as a function of volume for these harvesters, again based on the simple analysis we've done earlier in this slideshow, at two different frequencies, 1 Hertz and 10 Hertz, so we're perhaps talking about a body type of application here. And people are always talking about, can I have a self-powered laptop, can I have a self-powered mobile phone, and obviously the watch is something that's well known, and the sensor node is always the type of thing in research that we're trying to make as a self-powered setup. So if you look at the total power you could get as a function of volume at these two different excitation frequencies with 1G acceleration, then the total power requirements of the watch are pretty low, down at the sort of microwatt level. But the total amount of power that you could actually achieve in the same volume as a watch, if you made a harvester the entire volume of a watch, then you would be able to get milliwatt levels of power. If you want to build a laptop, which is a self-powered laptop, then clearly the device is bigger, sits somewhere around here. But what this is saying is, and the sort of power levels that you require in a laptop go up to around about 10 watts, so it's sitting at about 10 watts here. But that's actually the total power generation capability of something in the same volume as a laptop. So if you built something that was the size of a laptop and it was 100% energy harvester, it didn't have any computer in it, it was just an energy harvester that was the size of a laptop, then the best you could do under ideal conditions would be to generate the amount of power that the laptop required. So of course now your laptop's twice as big because half of it's harvester, half of it's laptop. The watch, that's not the case. The watch, you can generate way more power than you need in the particular volume for the watch, which is why the watch is such a nice application for energy harvesting. And it's why the laptop, and the same thing for the cell phone, are really not good applications for harvesting, because you would need the entire volume of that device, or more, depending on if it was at 1 Hertz excitation, you'd need even more volume than the device is to turn over to harvester just to power that device. And the sensor node then, of course, is the thing in research that we're often interested in powering. It tends to be smaller than the wristwatch. Power requirements tend to be a little bit higher than the wristwatch, maybe going up to 10, perhaps up to 100 microwatts. So it sits somewhere here. It's a little bit to the left of the watch and a little bit higher up on here in terms of its power requirements. But crucially, it's still reasonably below what we can achieve in terms of a harvester, the same volume as we're interested in making the wireless sensor node. So it's clearly, you know, the closer these objects here get to these lines, the more difficult the scenario it is to make them self-powered. And you can see the watch is the furthest away from the line, so it's a great candidate. The laptop and the cell phone, there's no chance. But the sensor node is harder than the watch, but is still far enough away from these lines to mean that we can do it. So we really can produce self-powered sensor nodes as long as we design them properly. Okay, bunch of people that have worked on this technology with me over a number of years now, and a bunch of references here that you should have a look at your leisure. Okay, so let's talk a little bit about power electronics for energy harvesting. Now we've had a very brief overview of some of the aspects of power electronics there for the different types of harvester, and I hope that what you've really gained from that is the understanding, at least at the moment, that in order for the harvester to operate and get the maximum power generation possible within its mechanical domain, then what I've got to do is I've got to set up the harvester's mechanics properly, and a big part of that is setting up the right force on the transducer. If I've got the optimal force on the transducer, I'll maximize the power that I can generate into my electrical system. Now, what I need to be able to think about now is how I design the power electronics in such a way that I can really maximize that total amount of energy through the power electronics itself, and also to be able to control those parameters that I was talking about. I'm interested in power electronics typically in controlling the current in inductors and the voltage on capacitors. And so that can then naturally reflect into the harvesting domain of controlling the voltage on the piezo capacitance, the voltage on the capacitors in a moving capacitor type harvester, or indeed, if it's an electromagnetic harvester, I can control the current in the inductance of the harvester. And through all of those techniques, therefore, if I operate the electronics properly, I can control the force properly to maximize the overall power that I'm capable of getting. So what I'm going to do here is, I've talked about the fact that in terms of the harvester now, you know something about the optimization. You know we have to optimize this damping force, electrical damping force. And I want to try and cover a little bit of sort of basics of power electronics to start with, before we look then at specific details of circuits for energy harvesting devices. So I'm going to try and cover something about, again, the more detailed view of piezo, electrostatic and electromagnetic interfaces. But ultimately, we're interested in powering a low voltage DC load from whatever the harvester is actually producing. So we end up with this type of system. This is a slight modification of a diagram you saw in the previous talk. Transducer. In our case, motion is going into this transducer. The transducer within this project is going to be piezoelectric, but it could potentially be the moving plate capacitor or the electromagnetic approach. There's an interface circuit, the first bit of our power electronics there, which is going to get the energy into the energy storage unit, and therefore there are two roles that interface circuit has to play. It has to do rectification to get an AC into a DC energy storage, and it has to make sure that we get the right force on the transducer to maximize the power density. That energy storage element, as I said, the voltage could potentially be going up and down, so we want some post voltage regulation there before we power our load electronics. So this is a piece of power electronics here which has got to look both back at the transducer and forward to the energy storage, and this piece of power electronics here has got to take a variable voltage from the energy storage and convert it to something that is the right voltage for the load electronics. So in terms of what our power electronics for our harvester has to do, the absolute must-have features, of course, it's got to extract energy from the transducer. It's got to provide it to the load at the right voltage, otherwise the load is simply not going to work. So to do that, it's got to do rectification, and it's going to have to step the voltage up or down. We probably got to have energy storage, as I said, because the vibration source in this scenario is probably going to be intermittent, so we need to have energy storage to cover when the system is not being excited by the vibration. And then the other features that I've put here as kind of nice to have features, but really, we really would like to have them, that power electronics has got to enable us to maximize the electrical power, and therefore it's got to be able to set the right force onto the transducer, which means setting the voltage if it's an electrostatic device, or setting the current if it's an electromagnetic device. And another thing that we might want to do that we haven't really talked about yet, but this is something that certainly on a vehicle application could be very important. If we want to have a resonant device, and we might want to have a resonant device, as I said, if the vibration is much smaller in amplitude than the size of the device, we get significant benefit from resonance, but only if we're operating at the resonant frequency. So what do you do in your car if you're going to drive at different speeds and the resonant frequency, the frequency of excitation is changing all the time? It'll be a different frequency of excitation if you're doing 70 miles an hour on the motorway to if you're doing 10 miles an hour in town. So you might want to have some adaptation into the harvester, able to tune the resonant frequency. And that's something that you might be able to do mechanically. You might be able to change the spring constant of something mechanically, but you might be able to do it electrically as well, because we've seen you can alter the force on these transduction mechanisms in an electrical way. So perhaps we can mimic a spring by doing something electrically as well, and then we can tune the harvester. Okay, so that's probably a very good point to break now for lunch. What we will do when we come back from lunch is start with some fundamentals of power electronics. So we've talked kind of a bit vaguely so far about this sort of nebulous thing called power electronics. We've talked about these things as being circuits which can process electrical energy, and we've talked about it in the context of a harvester where it's got to be able to do rectification, it's got to be able to set an output voltage, it's got to be able to control the way that the harvester mechanics works. But we haven't really got to the sort of nuts and bolts of how you build a power electronics circuit, how you analyze it, what the basic building blocks are. And once you know those basic building blocks, looking at these more complex specific circuits for harvesters will be much easier.